All right. So, onwards. I want another wonderful lecture and a rainy day to keep you inside. So, no sad faces now, because there's no reason not to be inside with me. All right, and Fabrizio's gone to get my clicker. I forgot my clicker, so I'm a little bit tied to the computer over here for a minute. So, let's get this thing rolling. There we go. All right. So today's topic is infrastructure. We're going to do a quick review of infrastructure, give you a brief introduction to track and signals, and then talk about how that influences the running time of the train, how that influences getting the train over the network and where it's going. So we're going to talk about that today. Quick review. So last time the key, yes? I could, or he's going to be here any minute, and I really appreciate that thought, though. Oh, that's not me. He's coming. I know he's coming, but I appreciate it. I know if I grab yours and I use it, I will forget to give it back to you in the class, and then we'll really be goofed up. So I will just tough it out here for 10 minutes, and then when he comes with the real one, I'll use it. But I appreciate that. Thanks for that emergency backup there. You got my back. All right. So the key piece of information, other than the basic introduction, and kind of a nice soft history introduction to railways last course, was economics. Talking about the economics of the railways. What is significant about the economics of the railway? Economics of railway transport. What makes railway transport special economically? What is special about railway transport? Miguel, save your job. What's special about railway transport?
That it's a very strict network.
Yes. That's in terms of operational constraints, in terms of how we operate. What economically is special about the railways?
You can
carry heavy load. It's another physical thing, but how is that financially? What's financially special about the railways?
The amount of the load or the price of the load compared to the price to the costs of the route.
Okay,
Yes.
we're getting closer. I think you got the thoughts coming out. You're trying to put it into words. What is she trying to say? Yes?
So it doesn't allow for competition and parallel routes and stuff like that. So if someone wants to get something shipped from A to B, they want to ship it by rail, they
Well, we definitely have monopoly forces. We have a lot of issues in pricing and service delivery in railways. We have oligopolies. You have monopolies and oligopolies. You have definite price coercion. You have a captive shipper. What is a captive shipper? It's not a pirate slave. What is it? Captive shipper. What is a captive shipper? A captive shipper is a shipper who, like you said, Sean, has no alternative. If you have a railway line that runs up to a mine in the Colorado Mountains, and that mine is taking silver out of the ground or lead or things or something, and you've got to ship it, that's a captive shipper. That mine has no alternative. That mine has no other way to ship that material than your railway. So that mine is a captive shipper. Another captive shipper would be a coal mine. And a captive, not quite a shipper, a captive receiver would be a power plant, electric power plant. The United States, enormous quantities of coal are burned for electric power. Enormous quantities. Huge quantities. Freight trains of 100 cars, each car carrying something like 80 tons. So you got 8,000 tons of coal. Trains like that roll like streetcars through Montana. Literally, like every 10 minutes. 8,000 tons of coal. 8,000 tons of coal. 8,000 tons of coal. Just rolling down the track. You go to feed the power plants in the United States. So you're a power plant owner in the United States. You are a captive receiver very often for railways. And this is a big source of litigation and argument in the United States. And one of the reasons there's motivation for new regulation in the United States to re-regulate freight services, because the shippers complaining to the railroads take advantage of them. The private railroads are using their market powers to organize against them to limit their economic ability. So, captive shippers, but infrastructure. What we're going to talk about today, infrastructure. This is where the money is invested in railways. You're a railroad, you have enormous amounts of cash loaded into the track, the bridges, and the subgrade, and the infrastructure, and this is a fixed cost. And this is very different from an airline or a trucking company or even an ocean shipping company, because none of those other transport modes have anywhere near the kind of infrastructure investment that a railroad does. And this plays all kinds of games with the pricing structure. It means you have huge differences between average cost and marginal cost. And this creates political problems, this creates regulatory problems, this creates all kinds of crazy game theory issues in terms of how you price your services and how you deliver services to the customer. And this is an ongoing thing. It's been historically true, and it continues to be true in terms of how you manage the economics of railway and how you manage the pricing. So today, what are we going to do today? We're going to go through some of this mechanical technique stuff. We're going to look at some of the track, basic technical stuff about track, technical stuff about signals. For those of you who like model trains, you're going to have a field day because you love to play with the track and you love to switch around the arrangements and see how it works. You're going to have a good time. Then we'll round out the class with some math. We'll start doing some train movement calculations, start calculating how the train accelerates and decelerates and how we graph and describe the pattern of these trains on the track. Assignment 1 is due today. I will be collecting your assignments today. If you have any special issues or needs or concerns, please talk to me. But otherwise, for all the other normal aspiring students, I expect to pick up your assignments today. Collecting them on paper, unless there's some other issue, and we'll grade them and return them to you on paper. So, infrastructure, here we go. Did you find the clicker? Thank you so much.
What?
Yeah.
Did you solve it?
Oh, you did it. You got it. All right.
Did you solve with
All right. Excellent.
Did you solve with the
I didn't. It's
okay.
either it's working or it's not. I don't know.
Okay.
We'll see. I don't know. We'll just have to ring it here. All right. So, infrastructure, track. Let's talk about track. Lots of track. So you probably had model trains as a kid, and you probably had a little loop of oval track for your trains to go around, so you had a single track train. And we were going to talk about double track and multiple track and combinations of this. Single track railway. 70% of the North American railway network is single track. Much of the Norwegian railway network is single track. A great deal of the Swedish network is single track. In Denmark, I think I showed you a slide last week, and I said 50% of the track is double track, so that means the other half of the track in Denmark is single track. So it's something you have to think about, because single track has very different kind of dispatching concerns than your speedway, your double track speedway here in Copenhagen. The local bond up there north of Hillerød is single track. It's the minimum configuration, obviously. This is the minimum to build a track somewhere, to deliver service. Single track is the way to go. And very often then you need to have these sidings, and we'll say something more about that here in a few minutes. But you need to have sidings so trains can pass each other on the network. The single track, because you've got trains going in opposing directions, we'll learn later in the course, does significantly restrict the flow. Right? You take a big hit, you take a big capacity hit when you go to single track. But of course, if you're trying to provide service at minimum cost for some community, like this little pretty rural area up here, single track is the way to go. Double track. All right, so those of us living here in Copenhagen, this is what we see every day. We take the S-tow someplace, it's double track. You go out to Hillerød, it's double track. If you're to Lundby, it's double track. All these places double track. Very often, that also means directional running. They will dedicate one direction, one track for one direction of traffic. And so it's more like a highway. A double track railroad is a lot like a highway. So the trains are all going the same direction on the two separate tracks. The most common for dense running, all these different lines that you're familiar with here in the metro area are double track railways. And of course, this is kind of what the track diagram would look like. And then we might have little, what are called crossovers, places where the trains can cross over to the other track, either because they have to reverse direction or because there's some kind of accident on the line and they need to do some kind of switching around, or sometimes you get really fancy. We'll learn later in the course, you do some fancy things with running reverse direction to overtake and do meets and passes and things like this. And then you get to really heavy industrial, multiple track, high intensity lines. This is the Northeast Corridor in the United States, Washington to New York City. And this is in the region of Philadelphia. And so we have triple track. We have 1, 2, 3 tracks here. And you can get all kinds of combinations and forms. And there are places around Berlin and Hanover and Hamburg, and you can go there and there's like 4 tracks and 5 tracks, and you can see these enormous quantities of track. So then you start to get into these really complicated networks and capabilities of different flows of traffic and that kind of thing. Triple track bidirectional. How do I know this is bidirectional? The signal. So we got signals pointing each direction. So this track is signaled for both directions. So that means the dispatcher can route traffic on any of these tracks in either direction. Because you can see there are signals pointing forward and backward. So the trains can go either direction on these lines. This is the Burlington route out of Chicago. This is Burlington Railroad, Chicago.
Is the picture taken from top of the car?
It's taken from a dome car. It's a dome car. So this guy sitting in the front seat of the dome car looking forward on the excursion train. And if you've never ridden on a dome car, you better do it now. Take some of that Danish SU money of yours and go to North America, go to Canada and ride a dome car before they're gone. Because it's an experience you won't ever forget. The ability to be up above the train looking forward across the top of the train is quite a thrill. And these cars are old and they're life expired. And they're going to not be in service much longer. Via Rail Canada is going to start yanking these things out of service because they're all 60 years old at this point. They're life expired. But it's an experience you'll never forget. You'll never forget that experience. So, as I said, lots of combinations. I mean, you can play around with your American train set and make all kinds of train track combinations you want. And it just comes down to what kind of flows do you expect to see in a certain geographic area? What kind of money do you have to invest? And maybe there's some geographic limits, you know, like raw mountains or really bad tunnel crossings or something like this that limit your ability to drive the track where you want it to go. So, some more technology stuff here. Points. Points. These are, in British term, is points. And they call it that because of the pointy little things here, little switch points like that. And an American, North American term is switch. And the literal translation to Danish is switch. So, we'll go with switch because that's the closest we got to the Danish practice here in this class. So a switch to connect 2 tracks together. Again, we have lots of combinations, and you don't need to learn every single one of these. All you need to know is, if you can imagine it, it exists. All it takes is a welder and a good cutting saw, and you can do whatever you want. Lots of different track combinations. Basic switch, little switch on curve, double slip switch. That little animal, you can go any direction you want on that thing. Triple switch right there. This is technically called a crossover because it's 4 separate switches with a diamond in the middle, and it's a compact way to get lots of back and forth across the mains there. That's actually a light rail system. It's not actually a railroad, that's light rail. And then this little animal here, I just picked at random, but you can imagine all kinds of crazy special work. You see a lot of this in dense yards, in railway yards, or big heavy terminals, heavy stations, streetcar track, a lot of tram networks. You can see some really messy special work in the street when they're trying to move stuff around. But you imagine it exists. Bottom line is a switch is the way to route traffic on different lines. The passing loop, British term, passing loop. American term, the siding. Again, it's a place to pull the train off and meet and pass on a single track or multiple track railway network. There's an action, and here's kind of diagrammatically what it would look like. Here's just a draw of the network on paper. And the junction here. So this is a level junction. We have lots of tracks crossing at grade, at flat, and so that obviously has a lot of complexities there to manage. Keep the trains from colliding. When the traffic gets too heavy that this is no longer feasible, or no longer practical, then you start to build some overpasses. And you get what's called the flying junction here. The flying junction, and they're spending a lot of money on stuff like this in the United States because our network congestion has gotten so bad that there are a lot of major junctions with railway lines in the United States where, imagine a train that long, imagine how long it's going to tie up that junction if it was a flat grade crossing. So they're starting to build a lot of these to really free up the congestion in major cities. Stations. So the station We have the station and we have the terminus. What's the difference between a station and a terminus? What's the difference between a station and a terminus?
Terminal is the end.
Terminal is the end of the track. Terminal is the end of the track. So this is a terminus, and this is a station. The station, the tracks go all the way through, and the train can pull right through the station. The terminus, the trains pull in and stop, they have to back out. They have to be pulled out or back out to turn around to change their direction. So Grand Central in New York City is a terminal, because the tracks come in from upstate New York and from Connecticut, and they end, and the trains have to be pulled back out. They have to back out to get them out of the station. Whereas Penn Station in New York City is a station, because Penn Station, the tracks go through Penn Station. They go from New Jersey through the tunnel under the river, through Penn Station and out to Queens, and then out over Hell's Gate Bridge and up to Connecticut that way. So, stations and termini. Think about stations, and it's something important to bring to your attention, especially if you're reading a bunch of European literature or British literature. This term station is a legacy concept. You go way back in the old days, a station was a manned control point. There was a guy, there was an employee of the railway there who was in charge of giving traffic signals to the railways. And so there were lots of stations, and every time they needed a place to control railway traffic, they built a station house and they put a guy in the building, and they said he was the station master and he controlled the train traffic. So you'll see a lot of literature today where they still refer to every place that there's a signal on the track as a station. So you'll read these technical reports or this literature about calculations for how to do timetabling and this kind of stuff, and they'll talk about the station, and then they'll say, well, from one station to the next there's nothing, it's just empty track. That kind of thinking is an old legacy assumption, because almost no stations are manned anymore. There's no longer railway employees at stations anymore. Almost all signals are remotely controlled from a remote location. And in rural areas like North America or Norway or someplace like that, they've had passing sightings and signals out in the middle of nowhere for a long time without station masters on location. So just be aware that sometimes you'll read papers about timetabling, about mathematical optimization, and they'll specifically refer to how they only allow trains to meet and pass at a station, and what it's just a legacy vocabulary, and it doesn't really mean anything anymore. Let's talk about the track technology, particularly how it influences the train operation, how it influences train movement, and how it creates some special issues when we're trying to use common infrastructure, this hugely expensive infrastructure that we've invested so much in. And now we want to get the most out of it, and now suddenly we're stuck. Because sometimes the infrastructure itself is our own enemy, is our own worst enemy here. Look at this picture. The tracks have a tilt to them. See how the tracks have a tilt to them? All right? You go to Tivoli and you ride the Odin Express, and that thing's got a tilt to it too, right? Because if it didn't have a tilt to it, you'd have a horrible time going around that curve on the roller coaster, on the little train roller coaster at Tivoli. So real railways also have a tilt to them on curves, because that's the only way to get a comfort level for the passengers going on the curves. It also has a significant impact on things like wheel wear, the rail-wheel interface, and how the treads wear, and how the rail balances, and all that kind of stuff. So you have to have a super elevation to help the train go around the curve. Little problem here. The amount of super elevation is a function of the speed you're going to go around that curve. If the train goes slow, you don't want a lot of super elevation. If the train goes fast, you want a lot of super elevation. Now you want to mix two different speeds of train on the same track. You got a problem. If this track is super elevated for the high-speed train, when the slow-speed train goes around the curve, it's going to squeal all the way around the track, because the gravity is going to be pulling it down against that inside rail, and it's going to actually literally take little slivers of steel off the rail. It's actually going to shred it like a cheese cutter. It's going to send a little sliver of steel off the rail, because that heavy train is going too slow, and all of its weight is on the inside rail. If you leave the track too flat to satisfy the slower speed train, and then you put the super fast train on that, all the passengers are going to be like up against the wall like this when it goes around. You're going to feel like you're in a roundup at the state fair because you are not going to be able to enjoy your rides. It's very uncomfortable. Even though the train itself can actually survive that trip around the curve at a higher speed, it's just uncomfortable for the passengers. And so that leads to the tilting train. So the tilting train satisfies the passenger's need for comfort while allowing the train to go around a fast curve that has not been super elevated properly for that comfort level. And so a lot of technology has been spent, money investment has been spent on this, and this has been very successful. Our Spanish friends are leaders in this area, going back 40 years. The Talgo is the first commercially successful tilting train. Very good service, very good equipment. There's now Talgo equipment running in lots of countries, including Northwest United States, in Washington State and Oregon, to get high-speed service on flat curves with freight traffic. The Pendolino, our Italian friends, the next leaders in tilting train technology. So Italy, mountainous territory, really tough terrain, high-speed track, a lot of curves. A lot of curves in Italy because it's mountainous, Italy is a mountain country. So the Pendolino is an Italian thing. They have tilting trains to get the most out of their high-speed lines. And then our Swedish friends have the X2000, the most recent type of tilting train technology. And the X2000 is also the same technology that Amtrak licensed for their Acela train running in the Northeast Corridor. So a lot of tilting train technology out there. All of this, and you can see how the track is kind of relatively flat, and the train has artificially tilted itself extra. The train has actually tilted its body on the bogie to give the passengers a comfort zone going around that curve that they wouldn't otherwise have. Now, we're doing good here. I don't think, do we need a break? Do we need a break? Does anybody need to go to the bathroom? Coffee? No smoke? No? We good? Okay, let's keep going. All right. So, we make good progress. This is good because I think the exercise we have actually is going to consume some time. So I think it's good that I get through these quickly so you have lots of relaxing time to just do the exercise very leisurely, relax, go get the pub, get a beer, I don't know. I just noticed the pub for the first time today. I just noticed there's a pub. Did you notice a pub around the corner? I didn't know there was a pub around the corner. Yeah, dude, get a flight of shots and go for it. Anyway, so here we are. So we've just covered the track. Oh, and I didn't say this. I'll mention this again. I did not mention this yet at all, actually. So I just went through this briefly, right? If you're really excited about track and you want to know all about it, we have a whole course designed just around, because the whole semester just talking about track. And so there it is right there. So if you really want to learn about track, go. There you go. There's your course. And likewise for the signals, we're just going to kind of quickly skim across the top here, just get the basics. If you're really excited about signals, we got a whole course just on signals. You just go crazy. You learn about light bulbs and different semaphores, and how many different ways they say go, and all kinds of stuff. So you can do lots of that. But let's get the key elements here that are really influencing our problem. So we have kind of 4 fundamental categories of information about signals that you need to know. Number 1, there are passive signals and there are active signals. We'll go through what those mean. Passive signals are either going to be dark territory, which means no signals at all, in a way, or visual signals, which most of you are familiar with. Stoplights, lights of some kind of visual element. Then we have active signals. And I'm defining the difference between passive and active as in passive, you give a signal to the train, but it's the train's responsibility to do something about it. An active signal will actually interfere with the train's operation and do something to the train. So in an active signal, we have things like centralized traffic control, where not only are you given a signal indication, but centralized traffic is actually switching the track and changing your route for you. We have train stops. We have various types of train stops. So if you violate the signal, the train will stop. That's an active signal, reaching out and touching the train. Then we have interlocking. The idea that we cannot give a signal indication unless we know for a fact that it is in agreement with all the other signal indications that we've given on the railway line. And so we'll briefly take a look at these. And then at the very end, we want to distinguish between discrete and continuous signals. discrete and continuous. And we'll see more what I mean when we look at that in a few minutes. So dark territory. A lot of railroads are dark territory. A lot of North American railroads are dark territory. Dark territory means there are no signals. There are no signals. And you have very little communication. There are large lengths of railroad in North America where the only communication is radio. Dark territory, and you have radio. And it's broadcast radio. It's not some fancy GSM stuff. It's like you pick up the radio, and it's like CD on the highway, and everybody else can hear what you're saying, and you can hear what the dispatcher is saying. And if you're a rail fan in the United States, you can buy a scanner and just listen to the rail fan, listen to the dispatcher traffic, and just listen to what the railroad engineers and dispatchers are saying to each other. You can just listen to it. So this is dark territory, and this is no longer done anymore because this has all been replaced by radio. But this is visually and symbolically what is done by radio now. This is a train order. This is train order territory. This is a station with a train order clerk working the station who is receiving commands from central dispatch by telegraph, writing them down on paper in triplicate with carbon, and then he's got a hoop. He's got a big cane rod or a wooden staff with a hoop on the end, and he has attached the written orders to that hoop with a rubber band or a piece of string, and then he's holding it up to the train, and the engineer is going to come with his arm out and keep it up as the train's moving, so the train doesn't have to stop. He's going to pick up those orders, and he's got another one in his hand because this is the days of the caboose. So we have the engineer here with this order set, and this order set to the conductor. The conductor's the back of the train, the caboose. The conductor's going to hang outside the caboose and pick up his orders too. So we have two sets of orders for the front and the rear of the train. And so the engineer's going to get these orders and open them up, and the orders are going to give him authority to go somewhere. And they're going to be very explicit. They're going to say things like, you have the authority to go to this milepost on the track. And when you get to that milepost, you have to wait for this other train. And the other train is going to be this number. And when you've met that other train and that other train is passed, you now have authority to keep going, et cetera, et cetera, et cetera. And these orders can get really complicated because they're like, sometimes they really can be messy. I mean, I'll just give you an example. It's still in practice, although it's with radio and stuff today, it's a little more not so complicated, but it used to be stuff like you would get a train order that would be something like from here, you have the authority to go this way, and you have the authority to go to this place up until, like 7:45 a.m. And if you don't get there in time by 7:45 a.m., you got to stop and wait. And then you have authority to go to this place up until 8:15 a.m., et cetera, et cetera. And they would issue these timed authorities. And they would give the other trains in the line similar timed authorities. And as long as everybody respected their timed authorities, everything was great. And then something went wrong. Somebody didn't read their orders correctly, or they mistook their orders, they didn't understand what they read. There's a little complication there, and that's how you get train collisions. You get trains crashing into each other. Now, today, this is a lost art. Nobody does this anymore. This is like telegraphy, Morse code, train orders. It's all gone. Nobody does that anymore. But it's now replaced with something called track warrants, which are essentially the same thing issued by radio. So the dispatcher gets on the radio, calls the train crew. Train crew guy has a pad of paper, and he writes down the order dictated to him by radio. After he's finished writing it down, he picks up the radio and he has to recite it back to the dispatcher, spelling out all of the city names and spelling out the train numbers and spelling out the mileposts, so that they confirm that the orders are correct. And then they go by train order that way with the radio traffic control. So that's still very common. You have a lot of dark territory in places where you're running trains by radio command, and you have to be very careful because all it takes is one goof up, one mistake, one misunderstanding, and these trains will crash into each other. There's no other safety, there's no backup. There's no other safety backup for this kind of stuff. And unfortunately, in modern times in the United States, you still get train collisions. You get head-on train collisions. And they don't make the news a lot because usually they're just like a giant freight train and the only people that die are the train crews, so it doesn't rank, you know. Once in a while though, it's a passenger train and it's pretty nasty. And I'll mention some more about that here in a minute. Then we have visual signals. These are visual signals. You see these all the time. You see these on trains here in Denmark, color light signals. The earliest visual signals are semaphores. They are physical movement signals. They're physical signals that have a physical moving part. Why do they have a physical moving part? Why do they do that? Somebody has to move them. Somebody has to move them. So before electricity, when we didn't have electricity, there was a guy in a signal box with a big row of levers, and these levers were attached to wires. And this wire, or in the case of the United States, long half-inch iron pipe. We didn't use wire. In Europe, we use wire. You use wire and use a gravity system to move everything. In the United States, we use a half-inch steel pipe or iron pipe. And so you push and pull the pipe. And in Europe, you pull the wire, and when you let go of the wire, a spring or a weight the other end pulls it the other direction. But anyway, either way, it's a mechanical movement. You got a guy pulling the lever, and he's literally going to move this lever, and the mechanical force is going to get transmitted up the track, 300 meters, 500 meters, some part far away. And that's another reason why you had to have a station every time you had a control point. There had to be a guy at the station in the station house pulling these levers, and they can't be very far apart because there's only so far a piece of wire can go to pull the signal. So you have this guy pulling the levers, and that's going to move the semaphore. He's going to pull it mechanically and change the semaphore position of these levers. Well, this thing called electricity came along, and suddenly we had some more flexibility. And so the first step they did was they electrified the semaphores. So they installed little electric motors in the semaphores, and they moved the semaphore up and down with an electric motor. That was a big help, because now we didn't have to have the signals located in close proximity to a building with a man employed inside. And then we started adding electric light bulbs. So we first added a little electric light bulb to the semaphore to light up the semaphore. And then we kind of migrated to the position light, where it's all electric and it's all light bulbs, but we're still doing this position thing, where the signal indication is really about a physical position and not the illumination. Why did they do that? Two reasons. Why did they do that? What's this business about this position light stuff? That's crazy. What's that all about? Why are they doing it? What are they doing that for? Well, why don't you just go straight to the light bulb?
To direct the train?
Sorry?
To direct the train?
I mean, why not a colored light bulb? Why not yellow, green, you know, it's no big deal. Colored light bulb and you're done with it. Why position light?
If the light goes off.
Yeah. So the early light bulbs are not very reliable. Right? They burn out quickly. You can't trust how long they're going to last. So with the position light, you have multiple light bulbs. If one of those bulbs burns out, the engineer knows the signal is malfunctioning. That immediately, in the rule book, that immediately becomes a stop signal. You don't, even if you know it's the right signal, you don't go because you know the light's not working. Something's wrong. You stop. You wait for dispatch authority to proceed. Somebody, the signal maintainer gets informed and they change the light bulb, this kind of stuff. Second reason, why position lights? Why position lights? Why not just red, yellow, green?
To follow the old system?
Partly to follow the old system, so why is the old system like this?
When you have this arm moving,
Yeah.
Easier to distinguish the distance.
Issues of visibility, color blindness. Color blindness. Now today they test employees for color blindness, and I think unfortunately it's an excluding condition. If you have color blindness, you can't be irrelevant. So, I had a job. I told you this last week. I had that job on the summer railroad. And one of my jobs as a crew member, as a fireman, was to validate the signal when we were coming around the corner. Because two reasons. One, the signal rules tell you to do that on an old traditional railroad train with two crew members in the cab. The two crew members have to both see the signal, and they both have to verbally tell each other they saw the signal and confirm they saw the signal. So on this railroad, we had a signal in the middle of the line where there was a junction where a passing side where two trains were meet each other. And the signal for the passing side, the back of the signal was a hill with a great big rolling green field of corn. You know where I'm going with this? So it's a searchlight signal. A searchlight signal means it's one light bulb. It's one light bulb, and it has lenses inside that flip to change the color of the light bulb. So different colored glass to change the color of the light bulb. So it's a searchlight signal, behind it of which is a great big field of corn. And this is June, and the corn is green and golden and beautiful. And unfortunately, though, my eyesight wasn't the greatest. I mean, it was okay. It was legal to get a driver's license. I could have a driver's license without glasses, but it wasn't pure 20/20. It was like, I don't know, whatever it is, 30/20 or whatever you call it. You know, it was like just a little bit less. And coming around that corner, looking at that field of green, with the searchlight signal in front of the field of green, I could not see the green light bulb. All I saw was the black searchlight mast and the green corn behind it. And when the light was green, I could not see it because the green corn behind it masked the light bulb. And I have to admit, I can tell you this now because no one's going to get me in jail. But I learned at the first couple of trips, I told the engineer I couldn't confirm it yet, and he got angry at me. And it wasn't until we were closer down the hill that I actually could see the green light bulb. So that's the first couple of trips I lied. So I learned that when I couldn't see the light bulb, and then it was green, because there was a field of corn behind it. So whenever I saw the black signal mask and I couldn't see the light, I said, "Oh, it's green. Let's go." But it was, I mean, it was a, it was a good visibility hill and everything. So if there was anything wrong, you could still see the track further beyond that signal, so you knew what was going on. It was just a confirmation thing. But color blindness, it's a serious issue. And today, they filter out the employees and say, if your eyesight isn't good enough, we're not going to do that. And they do other things. They put bigger black boundaries around the light to really make sure that the light is clearly distinguished from whatever's behind you. So we finally get away to more reliable light bulbs, and so then you have pure color light. You have just pure color light signals. And then they still have multiple light bulbs, but the reason is not because you can't see them. The reason is because they use these combination of bulbs to give more indications, right? So with just 3 colors, you'd have 3 different signals: stop, caution, go. But they add like an extra light bulb or a second extra light bulb, and you get all these different combinations like, well, kind of stop, or kind of go, or go a little bit, but not too much. And you get all these different combinations, and there's a million rule books, different countries, different railroad lines, different kind of rules, but they all come down to memorize these combinations, and they give you different levels of authority about how much you can go and what you will expect at the next signal. So there's just kind of all these different abbreviations. And they're pretty easy to just memorize it for the different lines that you're on. So visual signals are great, but they all rely upon the people in the locomotive, in the train, to obey them. They're only as good as the people looking at the signal, and only as good as the person obeying that signal. So they are passive. They do not actually have any authority or control over the train. So the next level of control is centralized traffic control. With centralized traffic control, there is actually some monitoring of the trains on the network. There's actually a control board which actually has a track diagram, and there are actually little light bulbs on the track diagram, and if there is a train on the track, the light bulb lights up and says there's a train on the track. So you have, this is, for 1920, this is high tech, right? I mean, this is, wow, we know the dispatcher knows where the trains are. The dispatcher is not dependent upon the train operator either radioing their position in, or in the really old days, waiting for a telegraph message from the station telling them that a train has gone by, which really slowed down the response time. So the dispatcher can immediately see what the positions of the trains are, and the dispatcher has the ability to throw the switches. The dispatcher has electrical control to throw the switches, and the dispatcher has very often then, in combination with this, the ability to change the signal indications to match the path they were given the train at various levels. And so this is very active. This is much more active involvement in the operation of the train. And here's a relatively modern, this is a CTC board, probably from like 1940, 1950, but it's in operation at a modern time. You have the radio. This is probably a photo that could have easily been taken anywhere from 1980 to 1999. radio, train radio, clock on the wall, kind of replacement squawk box for the radio here, a few modifications to the CTC board, but basically 1940 CTC board in service here on Relic. So all of this, we've got CTC, we've got visual signals, all of this brings us to the question of, well, what does the signal mean? And how do we determine what that signal is going to mean? So we have to have discrete blocks. Just like you have a street light that's on the road, out here in front of the school or down at Moonby, you've got to have a street light, and that street light refers to a specific intersection. You have signals on the railway track that refer to specific chunks of track. And so we have discrete blocks. We have discrete blocks of authority that the train can follow and move it on the track. And so installation of the signals is, permanent. You're not going to move these things around. I mean, they're in concrete. They're bolted into the ground. They're not going anywhere. So these are fairly permanent decisions. When you design the line and you install the signals, you are committing relatively permanently, until you want to spend another couple $1 million. You're making a relatively long-term permanent decision about what is the size of the blocks on the track and what is the flow going to be over time. And it creates a number of interesting problems that you run into. So you have discrete blocks, you have finite track permissions. Typically, as we'll see here soon, signals operate in a 2-block separation pattern, which means you don't get a green until you are 2 blocks back from the preceding train. Because usually the blocks are designed in such a way that if you have a red signal, the block is long enough that the train can come to a stop at that red signal. So that means the train has to be warned in the previous block that the red signal is coming. And then therefore, you can't give it a green signal until you're 2 blocks back, because you have to have a green signal, then a warning that you're going to stop, and then a stop. So it's a 2-block separation. It's darn near standard on any railroad system in the world. And then that leads to a problem with something called signal wake. So signal wake is when you're riding the yellow of the preceding train. The train in front of you is slow for some reason. So it's a freight train. It's underpowered. It has a stopping schedule that's busier than your train. And so it's running slower than you are, and you are able to go faster, but you are constantly riding the yellow block behind the train in front of you because you can't get around them, and because you're stuck with this two block separation behind the train in front of you. And so this is a major capacity problem, especially if you have a stopping pattern of stations. You could, in some situations, be riding this yellow block when, in fact, maybe you kind of would like to get to a station that's a little bit closer up here, but you can't get into that station quickly enough because you're riding the yellow behind the slow train in front of you. And so we'll see a reason to get around that here in a minute. But this is where we get into discrete. We have intermittent data. These track positions are going to be the little light bulb on the CTC board, and they're either on or off. It doesn't say the train's at this milepost. It says the train is here or it's not here. So we have intermittent data in terms of train position, and we have signal blocks that create discrete chunks of data. And so we now have this signal wake problem, and we have this intermittent control of the train. So here's to talk about the design of the blocks. I was saying we have this curve, we have this deceleration curve, and we typically have to design a block so that the minimum dimension of the block, the minimum, now you go to some rural area like North America, and the blocks are much bigger than this deceleration curve because we're way out in the Wild West and there's plenty of space and the train volume isn't high enough to justify short blocks. But in the urban areas, the short block has to be at least as long as how long it takes to bring the train to a stop from the last signal indication. So that is a fundamental constraint on how big, how large the block is going to be. And then we can kind of monkey with this a little bit. There's some things we can do to improve this. We have all those funky different color light combinations to get some more information to the engineer. This is essentially here the lost time and energy, because what if you came to here, you got a yellow, and you think you're going to stop, but from that point forward you don't get any information until suddenly you get to the next signal, and in the time you were traveling, something changed. And the dispatcher changed, or the train in front of you got out of the way, or something changed, and suddenly you get a green signal. Even though you thought you were going to get a red signal, you would have had to have been decelerating all that time in preparation for the red signal. And then suddenly say, oh, I got a green signal. And then wow, you've done it. You put the throttle back open and you start going again. But this is all the lost time and energy due to that discrete information. Intermittent, discrete information creates inefficiency because you are doing things, essentially this becomes a little zone of dark territory here. After you pass that signal until you get into the visibility of the next signal, you are in a dark zone and you don't know what's happening. So this is a fundamental inefficiency of the block signal system that you can't do much about with this technology. We do, in some urban areas, in expensive installations, they try to fix this with something called the distance signal. They make a clone of that signal. They wire it to the same color, so it's the same indication. They make a little funky sign on it that says, hey, hello, this is just an advance warning of the signal that's coming up. They move it physically down the track to give the engineer some advance warning of what the signal indication is going to be. So this is an attempt to get rid of this inefficiency issue here. The problem with this is that you do this too much and you end up with a solid stream of lights going down the track. Because you can only do this so much before you just, put an enormous amount of wire and confused everybody with so many different signal indications. So then we have something called the active signal. So we have passive signals. Passive signals, we're giving the visual indication. We have the block control. And we have to worry about stopping the train. And now we have something called the active signals. So this would be like automatic train stop. So the very earliest forms of automatic train stop, there are examples of this in Europe. They're all very similar to what you're looking at here. This is a North American locomotive with a little signal indicator pickup. It's a little magnetic coil mounted on the wheels. And it's going to roll along. There's going to be a big electric magnet on the track. It's going to energize this coil as the train goes by and pass some kind of a piece of information to the locomotive. And in Europe, you have similar things. So the French have this thing called the crocodile. It's a little wavy, funky thing in the middle of the track. And when the train goes over, it picks up an electric signal and transmits some information. There's other railways. If you're riding the S-tow here in Denmark and you look down the track from the platform, you'll see two giant extension cords running along the length of the track. And that's actually a big antenna loop that transmits information to the train along the length of the track. So it's the same kind of idea. But automatic train stop is intermittent. It only happens at these pickup points in front of the signal. And it's very basic, and it says if the signal's red and you're still moving, the brakes are going to come on. So it's a very basic kind of safety interface to stop engineers from going through red signals. The next level above that is train control. Train control, and that adds a longer data connection so that the train is in longer communication with the signal, usually through some kind of a coil loop or some kind of an electrical signal broadcast by radio or something, and that adds a speed supervision. So all of the modern kind of TGV and high-speed trains from the 1960s on all involve some kind of train control where it's not just train stop at a red signal, but the engineer's also given a slap on the hand if he's going too fast for a curve. If the curve says 60 kilometers an hour and he's going 80, automatic train control is going to send off a siren in the cab and say, hey, you're going too fast. And he's got to slow down or else he's going to get a brake application forced on him by the train computer. So automatic train control is pretty much mandatory on any kind of modern passenger or railway network anywhere here in Europe. And that brings us to the concept of continuous signals. So we have this business about discrete blocks and intermittent data, intermittent signal information. So if you go to automatic train control and you have a better data link between the train and the ground, then the next logical step is, hey, let's use that data link to put signals in the cab. And let's tell the engineer what the signals are continuously. And so this is goes back. You've seen this installations as early as 1930. The Pennsylvania Railroad in the United States and some other railroads. And I can't quote you the historic installation dates here in Europe, but I'm sure there's a similar time frame. But starting in the 1930s, they started installing cab signals in really high-density, expensive networks, where the engineer in fog or bad weather, or even when he's not inside of the signal, has an indicator in the cab telling him what the next signal is going to be. It's a huge improvement in terms of that efficiency curve, in terms of, well, is the next signal red or not? And do I need to start braking or can I keep going? This kind of stuff. So it has a huge improvement, eliminates all that expense of distance signals. You don't have to put all those distance signals in the ground anymore because the engineers got a continuous cab signal in the cab. So the continuous signal system is cab signal. And then that takes us to, hey, this whole fixed block thing is really bugging me. Can we do something about this? And there's this modern concept of movable block. Now, I don't think we have a system. Fabrizio, correct me if I'm wrong. Is there anywhere that actually has movable block in service today?
Not ERTMS. Maybe on the metro system they have the movable block.
Do they have movable block on the metro?
In Copenhagen they have. I don't know.
Really? Maybe? It's a lot of people dream about this movable block stuff, but this is high tech. This is theory. This is like not really quite ready for prime time yet. This is not here. But it's the next greatest thing, movable block. And that is the idea that we're going to not have these fixed blocks at all. We're going to go to cab signals. So we're going to tear out all the semaphores and the signals on the roadway. Just tear them out and throw them away. We're going to only have cab signals. And we're no longer going to have a distinct marked block on the track. And we're just going to say, hey, as long as you're not too close to the train in front of you, you can do whatever you want. Eric?
Would that interfere with ERTMS in some way?
Is ERTMS is ultimately compatible with moving block, isn't it? Because I mean,
But it's still
not yet.
divided.
On the third level, there is not yet implemented. It should.
there's nothing to stop you from doing it, but I don't think they've got a game plan to do
They
it.
will still have division by block.
Well, because
That's
ERTMS
kind of
at the top level,
Yeah.
it's radio, no signals on the track,
Yeah.
all cab signals,
And the technology.
and all supervision, complete continuous supervision. So from the train's point of view, there's nothing stopping you from going movable block because there's nothing else. It's all about computer software and how you program the control systems on the ground. Because from the train's point of view, we're jumping ahead here in conversation. We're talking about ERTMS, which I haven't even put up on the slides yet, but we'll get to it in a minute. But the bottom line is, the bottom line is it would support it in the future without a new investment in stuff. Yeah. So the logic behind this is if we can go to movable block, we completely eliminate any constraints whatsoever from being stuck into these rigid, discrete blocks of track and having to follow these rigid patterns. This is theoretical paper stuff. No one has this working yet. This is, except for a few rare exceptions, it's really not in service anyway. So for an example here, here we have our fixed block. We have this mandatory 2-block separation between trains. And the idea is here, well, I could let this train scoot up here and really hover right in the yellow block of this other train in front of me and crowd it the whole way. Because the movable block would always tell me immediately if that train slowed down or stopped. The movable block would say, you slow down or stop. And so it would be much more like highway traffic. A lot more like highway traffic where you're driving and you're hovering right behind the car in front of you and you're just waiting for that guy to tap the brake light. When you slow down and tap the brake light, that same kind of vision. That's a lot more what movable block would allow. Still kind of high tech, still kind of in the future.
Then again, it would be more autonomous with no driver, maybe.
Well, those are totally separate things. You can have no driver and fixed block and discrete and all that kind of stuff. We already do.
Yeah, but
There are plenty of systems that are no driver, that are old style, rigid blocks, track. The BART system in San Francisco is driverless. The subway in San Francisco is driverless. There are crew members on the train, but they do not drive the train. They only supervise the doors and they do passenger communications. But they are only for safety. They are only for customer service and safety. They do not drive the train. So the Bay Area Rapid Transit, all of the subway system in San Francisco, Oakland, San Jose, Richmond, San Rafael, all of that is driverless. And also things like the Vancouver SkyTrain is driverless. And then of course our Copenhagen Metro is driverless. Completely driverless. I mean, driverless and there's nobody on board for customer service. I mean, there's nobody there working the doors or anything like that. It's way, way far. So that takes us to what is the cutting edge in signals? What is the cutting edge today? What is the cutting edge? So the cutting edge would be active signals, signals that are actively involved in touching the train, actively supervising what the train is doing, number one. And two, continuous. Signals that have continuous control of the train, continuous communication with the train. Active and continuous. That is a modern signaling system. What is available to fill that requirement? Well, today in Europe, the big thing is ERTMS. What is that? European Railway Track Management System, something like that. Traffic management system. So ERTMS, this is the big thing in Europe right now. Now, it's a little, you know, there's a little bit of grumbling and grunting because in some modern countries like Germany and France, this doesn't actually offer anything new and better than what they already have. I mean, if you're on the TGV from Paris to Lyon, you don't need this. We're done. It already has active signals that are continuous. It's a done deal. And the same thing for a lot of the German network, high-speed network. You don't really need it. But the problem we have overall is lack of consistent standards from one country to another. And the inability to run international traffic because you don't have the same signal system and the same electric voltage from the wire. And so you have real problems getting trains to cross borders because the equipment is too complicated. So this is a major deal that would really hugely connect the European continent together because it really supports international trains. It allows trains to run from country to country seamlessly without stopping. So Denmark is really all over this because, well, two lucky coincidences. One, Denmark is a small country and has no choice. And two, Denmark's signal system is a little bit old and kludgy, and so they're in a great position to just spend a bunch of money and throw it all out and start over. As opposed to France or Germany, where they're like, hey man, we just bought all these signals last year. I don't want to throw these out now. And they still got life left. But Denmark is going whole hog. The whole Danish country is going to go ERTMS in this current revival cycle in the next couple of years. So that's going to be a big deal. And then we'll hopefully kick the Germans in the butt and get them to do it too. And then the train will be able to run from Copenhagen to Hamburg without having to have any special equipment or having to have special wiring or all this kind of stuff. Go. And then in the United States, we have something called positive train control. And a big difference between Europe and the United States, positive train control is not a standard, it is a set of expectations that is federally mandated. So, and this all revolves from a really bad train crash that happened 7 years ago, 7 or 8 years ago in California. An engineer, maybe someone like me, probably was talking on his cell phone, but the engineer of a commuter train at a station pulled out onto the main line when the signal indication on the ground was in fact red. And he ran head-on into a freight train. It killed like 100 people or something like that. Just big plane and all this kind of stuff. And it just really, everybody just said, whoa, what are we doing right now? We got mobile phones and satellite and all this stuff, and why are trains crashing into each other? So the federal government passed a mandate in the United States that said by 2015, that's next year, 2015, all of the North American Railway Network had to have positive train control, which meant active signals that were continuous. The federal mandate specifies what the system's features should be, but it does not specify what the technology should be. And this has created a buffer of confusion and delay, and what has happened is none of the railroads have really implemented it. And so there's a big, giant pushback, and the railroads are all screaming and saying, we need time to do this, we can't do it, and we need an extension. And so they're likely to get that extension for implementing this. So in the USA, we have the same requirement, the same desire to implement active and continuous signals. We have a federal mandate demanding that the railroads do it, but we do not have one standard, which means it's very likely we're going to see multiple standards and multiple manufacturers in the United States for the default system. So who cares? Who cares about all this other than train geeks? So we care about this as a management person, as a supervising person. We care for safety, obviously. We're interested in limiting human error and keeping the trains apart from each other. And then from a customer service point of view, this signal choice and this infrastructure choice is going to fundamentally drive how fast can we drive our trains, and what kind of service can we provide our customers. And then capacity is going to be fundamentally driven by our choice of signal systems. This is a big deal. So from an economic standpoint, the choice of our signal system drives our ability to deliver return on investment. And let's talk about this, our little friend Little's Law, which we learned last week. Little's Law now applies to how the signal system influences capacity on the network. So last week, I told you Little's Law, and I said what? What did we use Little's Law for last week?
How much room?
Ursa? So we used it for the numbers of required trains on a network. So last week we solved Little's Law for the inventory part. We said, we know the rate of flow, we know the time, what's the inventory? That was our homework problem last week. Now flip it around. Now flip it around. Now we're going to say, here's the time across the network. And now we're going to treat the inventory as an input. What is that input? This is the input. How many blocks we have and the signal system we have determines the inventory of trains that the chunk of track can hold. More blocks, tighter blocks, more trains on the track at the same time is a higher inventory of trains. So we now have rate of flow equals inventory divided by the time to go through the network. So we have a travel time across this network. We have an inventory on this line, 3 blocks. We need a 2-block separation for safety. So it's 1 train for 3 blocks of track. We have an inventory of 1 train, and the travel time is 1 hour, so the rate is 1 train per hour. We have 1 train on the network, so this is a rate of flow of 1 train per hour dictated by this inventory and by this time cycle across the network. How can we increase that rate of flow? How can we get more capacity out of that railway network? How can we serve more customers? Assuming we can't speed the trains up, we're in the fastest we can go. We can't go any faster. So we've got to get more trains into this space. We need to find a way to get more trains into this space. Lots of different things I've suggested already in the slides that we could do to make that happen. Number 1, smaller blocks. This gets a little crazy because these are really tight blocks now, and I got to spend all the money on all these signals, but it does do it, right? Hypothetically, I make smaller blocks, more signals, I can squeeze another train in it. I now have the same network, same travel time, but I now can hold 2 trains in the network safely, and now I've doubled my flow. I have now 2 trains an hour because the rate of time is the same. I've increased the inventory. Little's Law says I've now doubled my rate of flow. And then the next step beyond that, if I don't have discrete blocks, is the whole movable block thing, right? So instead of these discrete blocks, I find a way to scoop this train up and get right on the tail of this train, the safest I can be, the closest I can be within physical reality of safety. And then use a movable block to keep them in a ghosting pattern, like that. And if I did that, you could kind of look at this diagram and you could kind of argue, you know, I think I could squeeze this one in too. Because if I could scoop that one up a little bit more, I could scoop this one and really follow its tail, then we could go to 3. So that's kind of the theory behind movable block. And if I can just really cram these trains in the network as tight as I possibly can, I'm going to increase the inventory. And if I increase the inventory and maintain a rate of flow, I've increased my capacity. And I've serviced more customers and more freight flow within what? Why am I doing this? What is the underlying thing that I'm trying to maximize my use of? Sorry? The track, the infrastructure. All those things that I sunk my money into, all that concrete and brick and steel that has lost money. I mean, it's gone. That money is spent, it's in the ground, and I got to get the most out of it. And I'm going to get the most out of it if I can maximize this flow and get as many trains rolling over that invested infrastructure in the ground as possible. That's going to bring modern efficiency and modern return on investment. And in fact, we'll see later in the semester, that's exactly what a lot of North American railroads are doing, a lot of European railroads are doing. To get the most out of their infrastructure, you get as much traffic rolling across that steel as you possibly can. You pack it in double-decker trains. Double-decker trains. Make a lot of money. Pack twice as many passengers in the same train. You just doubled your flow. Didn't spend any more money on track. Didn't spend any more money on barely anything else. In the United States, double-stack container trains. Double-stack containers, you just doubled your flow. Whatever you can do to pack as much flow as you can into the same infrastructure is a moneymaker. It's easy, it's low-hanging fruit. You get a lot of money out of it. All right, so we're going to take a break now. How much does this extra capacity cost? How much does this extra capacity cost? This extra flow that I've been talking about, how much does it cost me? Yes, Sean? Yeah, probably. Well, no, they have electric double deckers here, but I get your point. I mean, either way, electric or diesel, what do you think? Well, I thought you were going to line of block and burns more fuel. Or doing more fuel. A little bit, not too much, because your aerodynamics is pretty good. You go to a double-decker train, you're still pushing pretty close to the same, air push envelope air.
Increases axle load.
Axle load,
So on
higher
the track,
axle load.
track and wheel friction.
Okay, now, there's a lot of people here that don't know what trains are. What is axle load?
Axle load is how much weight is put on by, let's say, a cart, because a cart is like driven on bogies, and bogies are usually 2, 3, 4, whatever axles,
Yeah.
and that car weight is put on a bogie
right.
weight, which is then
Right.
distributed
So
to
this
the
is a
axle
technical
load.
term, right? So axle load is literally how much weight on each pair of wheels on a train. So steel wheel and steel rail, the heavier the axle load, the more kind of deformation of the rail underneath the wheel. Yes?
When they increase the double containers, they increase also the wheel?
No, very often the wheel diameter does not increase.
So
So you are doubling the
when
weight.
you're projecting the rows, should you project for the actual, like for one container? So how it's going to be like?
Well, you get a bunch of engineers together, and they all get under their computers and do finite element analysis, and they figure out how much deformation the wheel is going to put on the rail. And in today's day and age, we've got these modern alloys. The steel in the rail is way better than it was 50 years ago. So we have really high quality steel, and we do really, really high quality things with the wheels, do a little high tech stuff. People publish papers on how well they can do the crystal structure and the iron in the wheels, and stuff like this. To maximize this, because the wheel diameter is really not going to change. And we're going to double the weight on the wheel, and we've got to really make sure that the wheel-rail interface is still going to perform appropriately, because otherwise, using the old wheels and the old rail from 60 years ago, double the axle load, the stuff would just crack up. I mean, it would just crumble under the weight. So, a lot of things. How much does this cost? It really doesn't cost a lot. Signals, some better rolling stock, but as we learned in the prior week, most of the money in the railroad is in the ground. And we're gaining a lot of capacity for very little cost. How does this affect financial statements? It's great, right? Any financial enterprise, you're going to look at return on investment, return on capital, cash flow, all of these things that we're talking about, better signals, better management of the infrastructure, which is going to be the second half, and really the biggest next part of this course, because so far we've been talking about technology. And starting next week, we're going to stop talking about technology, we're going to start talking about intellectual brain power. We're going to start talking about you as a manager, how can you smartly schedule these trains and get the most out of the infrastructure given the technology that you have. So, but all of this is great because it's going to increase your return on investment and increase your profitability, all this kind of stuff. So what really limits the capacity of a line? What really limits, is there any limit to what we can put on a line? What is the actual limit of capacity on a railway line? What stops it? What stops it from being infinite? Safety? So pretty much what really limits it, really what limits the ability of a line to carry traffic is really ultimately the length of the train. Because if you can always make a train longer, supposedly, to carry more traffic, but there is in fact a physical limit on how long the train can be. Today, that physical limit is fundamentally two things. The strength of the couplers. The couplers are literally the couplers that hold the cars together, the train assembled together, the couplers. The strength of the couplers is a fundamental limit to the length of the train, and the air brake system. The air brake system, which is beautiful and simple and model of efficiency and magic, but it is based on the idea that we're going to pressurize air and sink down a pipe. And if the train approaches a mile long in length, it takes a very long period of time for the air reduction to happen from this end of the train to that end of the train. So the air brake system is a fundamental limitation on the length of the train. And so there are two ways to address that. In the brake technology, they're finally starting to talk about electrically managed brakes. Brakes that have an electrical signal that drives the brake signal down the length of the train. That's happening in the United States finally. The second thing is the coupler strength, and that's a trickier thing to do. That's a trickier thing to do. One of the reasons Europe has short freight trains, a lot of people want to say, well, we have short freight trains because the sidings are longer. No, that's not why. You have short freight trains because in many networks you still use the screw coupler. So the screw couplers get the buffers, you look at any train, you see three little buffers coming in, and then there's a little piece of chain with like a big hook, and the guy gets in there, he lifts up his hook and drops it down on the hook. That coupler is very weak. It's a very weak coupler, and it can only take so much force before it just snaps. So it basically limits your train length, because you can't have a train long enough to really put a stress on that coupler. The United States has a knuckle coupler, which is a big, heavy steel casting with a big, heavy knuckle, and that coupler has the ability to have a much greater pull force on it. And so that's one of the major reasons the United States has much longer trains. Russia uses the knuckle coupler, and so Russia has very long trains. And so that's a major thing, is to switch all the stock over to the knuckle coupler to get the train on. All right, break. All right, so we're making great time, so the pace is going to slow down, and I've only got a few more slides, and then it's just all activity, and you're done listening to me talk. So we just got a few more slides, and then we have activities. So what are we going to do now? So we've covered this kind of fundamental technological stuff about track and signals and what it means for the infrastructure, and now we can kind of get into some mathematics and talk about train movement and what that was train movement. So we're going to learn some basic skills. Really basic skills. I hope they're basic. If you don't think they're basic, speak up and tell me, because I'm assuming they are basic, and I'm kind of visualizing the pace of what we do on my assumptions of what I think is easy and what I think is hard. So if you think it's not hard, not easy, you need to tell me so that I'm aware that I need to slow down and take time on things. So today we're going to learn about the kind of the basic dynamics of the train, and then talk about how to diagram, how to visually draw the positions of the trains on the network, and then calculate some running time numbers and do some basic things there. So we just finished. We talked about signals. We talked about the intensity of communication, the track block dimension. We talked about how important that was. And now we're going to talk about how to visualize the movement of the train across the network within consideration of all these physical constraints of track and signal. So the basic skill we want to learn today is how to draw a string line. We want to know how to draw a string line diagram today. This is a picture of a string line diagram. The European term for this is frequently graphic timetable. You can also see it referred to in some literature as a time distance diagram, or a time exposition, all kinds of stuff, and I'm sure in different foreign languages it has all kinds of different names and literal interpretations. But it's called a string line diagram because it's like lines of string drawn between the pins on the map here. There's nothing stopping you from rotating this 90 degrees and looking at it a different way, but pretty darn universally in most cases, horizontal is time, vertical is distance. And so here we have a picture with a little helpful diagram key here showing the track diagram on the left, the locations in the vertical dimension, and time is that way. So we're looking at the clock time up here, and these are the train numbers, and these are the paths of the train in time and distance over the diagram. And in the old days, oh, thanks. Yeah, read that, do I? Read that. That would be important. It might be like my new lottery number or something like that. In the old days, dispatchers actually kept big paper ledgers, and they would actually monitor the paths of trains live on paper diagrams like this for their records, for their permanent records. And they would use this to plan their movements for the day and actually draw it in on paper to do this. Today, this can be done very quickly, obviously, by computer. And we also use this to plan the timetables in advance. So we'll draw this thing out and look at these pictures in advance to see how the network is going to be used. So basically, you look at these and the train's moving, and then it stops somewhere, and this is a station. It has a siding, maybe more than one siding, especially looking at this picture right here. I'm assuming it has at least 4 tracks, because we have 1, 2, 3, 4 paths intersecting in the same place at the same time, so there's got to be 4 tracks there. So these are all places where trains are meeting each other on the network, and then the slope of the line is a visual indication of how fast the train is moving. So obviously the steeper the slope, the faster the train is moving, and the more casual the slope, the slower the train is moving. So we want to learn how to kind of draw one of those, and I hope it's not too hard. I hope this is not a very stressful thing to do. So here is a basic example of how to draw a string line diagram. This is a piece of the train timetable from Chicago to Milwaukee. We've got 4 trains here. This is the distance, the timetable mileposts here, and it's a very simple thing to do. You just take a piece of paper or a graphing program and you mark the vertical axis with the milepost or the dimensional distances here, and you put some time scale on the bottom here, and you plot each scheduled stop for your train on the map, and then the diagram, and then connect it with some strings, some drawing lines here, and you can see the movements then of the pattern of trains. Now this is a very simple one. This is drawn from the public timetable for these trains, so I don't have the level of detail showing me how long the trains stop in each station. So this does not show, so there's no flat spots on this because I didn't put in the arrival and the departure. I only put in one time just to pass through. This is a double track line between Chicago and Milwaukee, so these trains don't have to worry about where they pass each other. They're just going. They don't have to worry about intersecting anything. But hopefully that's not too hard to figure out. You can pause and look at that for a minute, and you've got it in your slide handout you can look at too. But again, you just distance on the vertical, time on the horizontal, plot the points where the train is going to be, connect the points with a line, and that is your string line diagram. Let's talk about, if we're doing this, that was based on a schedule someone gave to us. Now let's say we don't have a schedule. Now we're going to start with no information, and it's up to us to figure out what the schedule is going to be. Well, one of the first things we have to worry about is, well, how fast can the train go? How fast can the train go, and how do I know it can go that fast? And what about starting and stopping? How do I get the train to start and stop? And how do I measure that and put dimensions on all that? Well, we kind of mentioned this before last week. Trains have really heavy mass. They're heavy things. They're going to take a lot of effort to get up to speed. If you ever loaded your bike down, go to IKEA, you buy a bunch of stuff, you load it in the back of your bike, you try to pedal home on your bike. Suddenly it's a lot harder to get up to speed with all that furniture on the back of your bike, and I know people love to do that here. Nothing more humorous to me than I'm, taking a little light walk through downtown Copenhagen, and there's a guy riding a bike with a set of 4-foot fluorescent light bulbs under his arm as he's biking along in the path there. Hope he didn't run into anybody. But a lot of things influence the acceleration capability of the train. The first and most obvious one is what's called the horsepower-ton ratio. The horsepower-ton ratio. Now, in metric, it's, you know, the kilowatt something metric ton, whatever, I don't know, ratio. But in us English speak here, horsepower-ton, English units, how much motor power does the locomotive have relative to the weight of the train? Obviously, the more motor power, the bigger the engine, the more power it has to get that, you know, just like a car. A cheap car has no small motor and it takes a long time to accelerate on the highway. Fancy, expensive Ferrari has a big, heavy motor, and light car, and it can just kick right up and go on the highway. So it's a horsepower-ton ratio. Next thing is wheel-rail friction. You have to worry about that. Could be a real issue here in Denmark. A lot of water, a lot of rain, a lot of moss, a lot of leaves, a lot of big fat slugs all over the place. And you add all that up, and you get some slippery track, and that can really have a big problem in terms of traction and getting the train rolling. And then passenger comfort. Sometimes even the train is capable of moving faster than is comfortable for the passengers. And so sometimes even if the train is capable of doing something, you don't want it to do that because it's going to make the passengers uncomfortable. And the same thing in reverse. Braking. Friction for braking. But something else that we'll see a couple of pictures here in a minute that's overlooked, quite honestly, frequently ignored in some of the presentations I've seen, is that that's not the only thing limiting your braking ability. You're also limited in your braking ability by the ability to dissipate the energy from the brake shoes. That even if you have maximum braking at the maximum friction on the wheel rail, you still have to back off. Because if you keep braking at the maximum friction of the wheel rail, your brake shoes are going to glow red and melt. So you can't do that. And train slack is a real problem for longer trains. It's a real problem. You can have a derailment precipitated by brake action on a long train. So adhesion, you know, this is some pretty basic scientific stuff. The wheel rail friction is low, and we're so excited about that because it allows us to move these trains cheaply with a small amount of fuel, and it makes it very economical to run. And oops, this is a problem because it also means it's more difficult for us to slow the train down. This limited friction also is an inhibitor to braking of the train. And you can compare the train adhesion. A bigger number is better. A bigger number means more grip on the road. So dry wheel, 20%. Wet rail with leaves. United Kingdom, bad day. Can really go bad. It can really drop off dramatically. And this seriously is the reason why sometimes train services get canceled in the United Kingdom. Is that the weather conditions are bad enough they cannot run safely, or they have to drop the service speed so far down that they, it just clogs up the line. Compare that to a car, compare that to an automobile, and a dramatic difference. And even when it's wet, even when you have a bad weather situation on the highway, you still have better traction with an automobile on the road than you do with a railroad train, railroad car. So we've got about 1/5 to 1/10 of the adhesion of rail versus road. So that's kind of a limiting factor. But as I mentioned in the previous slide, that's not the end of it. That's not the whole story. Because even this, as low as this is still pretty good, and it's still in many cases more braking power than you can safely manage on a train. For example, this is a sugar beet train from California going downhill. And this is smoke coming off the brake shoes. Because this is a long, continuous downhill grade, and this is a heavily loaded freight train, and this train is not limited by its ability to brake. It's not limited by the friction coefficient of wheel to rail. It is limited by the ability of the brake shoes to dissipate the heat they generate during braking. And if this train is braked too heavily, the brake shoes will seize up, they will glow. The brake shoes will actually start to glow. They get hot enough that they will actually glow in the dark, and they will deform in the process of bringing the train downhill. So then the wheel gets really hot, and then the steel in the wheel changes molecular structure because it gets so hot, and then you introduce cracks in the wheel from the temperature differential of the wheel heating up. So this is a case where you cannot brake the train even as heavily as the friction coefficient allows you to brake the train, because the fundamental limitation of the brake shoes to take the heat comes into play. So you have to pull back, you have to back off and how heavily you brake the train. The second thing you have to worry about is train crash. A long train, particularly in North America, but sometimes also here in Europe, especially the screw couplers and the buffers. Train with screw couplers and buffers, long train with screw couplers and buffers, the slack action, that extra buffer of movement, the ability of the cars to bounce back and forth with a little bit of movement between them, which is necessary so that they can navigate curves correctly and necessary to give a little bit of flexibility, means that over a long train you have a significant amount of dimensional elasticity as the train squishes together and pulls apart. And sorry? That happens too. Now, they don't have sleeper trains in Europe barely anymore, do they? So anybody ever been on a sleeper train? You've been sleeper coach, Mikkel's been on a sleeper coach. They're canceling that this month. Did you hear that? Did you know the Copenhagen sleeper coach is dead this month? It's over. No more sleeper coach out of Copenhagen. It's finished. Very disappointed. It's a fun experience when you can get it. Yeah, Deutsche Bahn is canceling. The City Night Line is canceling Copenhagen as a sleeper destination. They're only going to get them from Hamburg from now on. There's not enough. It's too expensive. The traffic's not there. But if you're on a sleeper coach, you don't want a sleeper coach at the end of the train. If you get a sleeper berth on the sleeper train at the end of the train, you're going to have the worst sleep of your night, of your life. Because the end of the train is going to actually fishtail. You're actually going to feel the train, the last car of the train, swinging back and forth as it bangs against the flanges and the rail and swings, because at the very end of the train it's whipping itself back and forth and there's no buffer pull force keeping the train straight at the back of the train. I did that once. I was in a sleeper berth at the end of the train. It was a horrible ride. It was horrible. But this is a derailment caused by slack action. This is a derailment caused by excessive braking. The engineer put the train into emergency, seized up the brakes, and the slack action of the train smacked up against the brakes applied at the front of the train, and then it caused the train to buckle and to derail. And so the train left the tracks due to slack action. So this is a real problem. With heavy trains and with a slack action issue, excessive braking can be a safety factor. So you can't just, you're not only limited by the friction coefficient, you're limited by very careful, safe operation of the train. You have to do a lot of things. So you are very heavily, and then finally, injury to passengers. You know, you can't brake a passenger train heavily because you're going to hurt people. People are standing up, they're in the bathroom, they're getting coffee, they're taking luggage down from the overhead rack while the train is moving. And you can't slam the brakes on that, you're going to hurt people. So all these things really fundamentally limit how fast you can brake a train, how fast you can slow it down. So we've got some equations that we're going to share with you. I'm going to pick these slides quickly, but then most of you have handouts, and Fabrizio is going to lead you on an exercise here in a minute. And we're going to first ask you to, I'll let him tell you all about it, but you're going to get some practice doing string lines, so we're going to use some fun examples here. But anyway, let me quickly walk you through some of these equations. These are what are called parametric equations. Parametric. These are empirically fitted formulas. These are not, these are not formulas that come out of a physics textbook. These aren't formulas like, amps times volts equals watts, which can be proven in the lab and are known things and this kind of stuff. These are empirically fitted formulas because there are lots of different little things that influence the behavior of a train's movement that all can't quite be fitted into one measurement. And there are lots of other little things like air resistance and peculiar behaviors of certain kind of rolling stock and the manufacturer's settings for how the motor runs and all this kind of stuff. And so these are formulas where we're going to give you a table of data for some of these input values that is specific to a specific train type. And these formulas then represent how that specific manufacturer's train is likely to behave given those input parameters. So these are fitted formulas in that they're only relevant to like a certain train kind in a certain kind of environment And and these are approximations. These are not going to be written in stone, that these are absolutely gospel. These are rough approximations of how you would expect a certain train to behave under certain parameters. So we're going to give you data for this and show you how to work these. But basically we have formulas for our acceleration. And we have these approximations. This data and this item, this item, and this item come from the data table that we give you for a particular train type. And then this is where you want to go, how fast you want to go. From a cold start, this is from stop. From stop to this speed, how long does it take for that train type? And then down here, likewise, from a stopping position, how much distance does it take you to get up to that speed here? And this again is going to be given from the data table, and this is given from the data table for that type of train. And then the other direction, stopping, a little bit uglier looking. How much distance does it take me to stop that train? And again, information that's coming from a data table specific to a certain manufacturer's train type. So these things, this braking ratio and this braking percentage, these are both things that roughly estimate the braking efficiency of the train. This one here is roughly a ratio between how much braking capability the train has relative to how heavy the train is. And this guy here is a ratio of where the manufacturer says you should be comfortable driving the brake settings versus the absolute physical maximum brake setting. Then this is gravity, just basic gravity, it's just a fixed number. And this is if the train's on a hill. If this is on, the train is on a hill going downhill. How steep a grade is it going downhill? And this guy right here is comes into play when I talk to you about the really long train. So in a really long train, you're standing there at the air brakes, at the handle for the air brakes, and you swing the handle for the air brakes, and there's this big whoosh if you're in an older locomotive that could vents right into the cab. There's this big, and the air is blowing around, and you're venting the air from the train line up the train. And if it's a long train, you start venting now, and it could be 20 seconds before the air vents from the end of the train. And it's not until the air vents from the end of the train that the train brakes the rear of the train actually apply. So this could be how long, this is how long it takes for you to get a brake application actually going in the train from the time you say go. And then similar for the stopping, again, similar gradient for the stopping. But I'm going to hand it over to Fabrizio, and he's going to walk you, first he's going to walk you on making a basic string line diagram without all this funky math. And then he's going to work through a lesson where we go back up and we say, hey, okay, that first string line was kind of naive, just kind of assuming the train was just magically going to move when we said it was going to move. Now we're going to back up and recalculate and take into account this acceleration and deceleration in the train. And so this will be a kind of a group exercise. You can work with your buddy or whatever, but I'll hand it over to you and let you give a little presentation here.